Hello everyone, I'm Emanuele Raso from the University of Rome Tor Vergata, and today I'm going to present you our work ABEBox, a data-driven access control for securing public cloud storage with efficient key revocation. Before that, I want to take a brief moment to describe the current situation about privacy and security in cloud-based services. Let's take two widely spread and commonly used services. On the left you can see the instant messaging, and on the right the file storage and sharing. On the former we usually have the so-called end-to-end encryption, which is probably the most privacy-preserving solution currently available. When we use a file storage service instead, we are used to upload our data in a clear form, but is it possible to obtain something similar to the end-to-end encryption? In a cloud-based file sharing service, we usually authenticate ourselves. Then, if the authentication is successful, we can upload our data and share a link with our family and our friends so they can access it. But what we are doing with this approach? We are delegating everything to the cloud provider, the access control, the data protection, the key management, and the synchronization. Most importantly, we are giving our data in a clear form. So we need to have full confidence that the cloud provider won't make any misuse of our information. A more privacy-preserving solution could be to store our data in an encrypted form and to privately exchange the decryption keys. In this way, we are decoupling the data protection and access control from the data provisioning, leaving only the latter to the cloud provider. We are also relaxing the trust model from a fully trusted to a semi-trusted one, meaning we only needed to perform the required operations and delete all data. But as you can guess, this solution is not scalable. In fact, as the amount of data grows, much more load is placed on the users, as they have to share more keys, encrypt more files, and possibly manage multiple groups. Also, there are significant problems related to adding or removing users. Attribute-based access control is one of the most promising technologies that can help solve most of these problems. As the name suggests, it is an access control that makes use of attributes. It associates an access policy with a specific resource, and when a user wants to access it, an authorization engine checks whether the attributes of the user, of the environment, and of the resource meet the policy. On the right, you can see an example. The policy says that the file can only be accessed by Bob or the IT department, but not before the 3 p.m. Then suppose we have 3 access attempts. The first from the CEO Bob at 1 to 3 p.m. The second one from Alice of the HR department at 27 past 3 p.m. And the third at 18 to 4 from Carla of the IT department. The only one who will have access will be Carla. But as presented, ABAC, Attribute-Based Access Control, is still a server-side solution, but we would like a client-side one. Attribute-Based Encryption is an asymmetric encryption scheme based on the concept of attribute-based access control, where the access control is embedded in the cryptography scheme. Specifically, ciphertext policy attribute-based encryption is the mechanism where the policy is attached to the file and the attributes to the user's decryption keys. Since the access control is within the cryptography, it's protected by its mathematical properties and not by the robustness of a server of any server-side solution. But since it's inside the encryption, it's static. So a very significant problem is how to revoke the access of a user. The only solution is to re-encrypt the file using a new policy, but this requires the providing of new decryption keys to the authorized users. Let's see how a file is protected. Usually, the most common solution is to apply the so-called hybrid encryption that you can see on the left. Since a file can be arbitrarily long, its content is encrypted with a symmetric encryption scheme, such as AES, and the used symmetric key is encrypted with an asymmetric encryption scheme, such as RSA, in order to facilitate the sharing process. When we need to re-encrypt a file, we just act at the blue level. Using our private key, we decrypt the symmetric key and re-encrypt it with a new public key. So we don't modify the red part, but just the blue part. But are you sure it's secure? In 2017, Meyers and Schultz presented in the paper linked here a very interesting attack called key scraping. Let's say you are an employee and you are about to be fired. You want to create problems to your company. Let's say you want to save all the company's data on your private storage. Probably this is impractical because of the large amount of data, but you can use a smarter solution. You can use your private key to decrypt the symmetric key applied to the different data files and store them on your private storage system. Then, even if your access will be revoked, using the classical encryption mechanism shown previously, you can just use the prefetched symmetric keys to decrypt the encrypted content directly, bypassing the re-encryption layer. Meyers and Schultz also provided a solution to this attack. It makes use of an all-or-nothing transformation, a mechanism that makes bits dependent on each other. So even if only just one bit is missing, you cannot recover the whole content. During the encryption phase, instead of acting at the blue level, at the symmetric encryption key, we act at the level of the encrypted content by puncturing, by selecting random bits and encrypting them with a new symmetric key. This key is then encrypted with an asymmetric encryption scheme in order to protect it. However, their solution is quite impractical in our scenario. You have to consider that we might have to encrypt an entire repository, and also many times. So, if each AB encryption or decryption operation is 1000 times slower than RSA, how long would it take to decrypt even a single file? Our solution to this problem is to make use of a reverse chain to derive the symmetric key used during their encryption operations. Using a reverse chain, we only need the symmetric key related to the last re-encryption, so we can retrieve all the previous ones just by applying an hash function. Thus, we only need one AB decryption to completely remove all the applied re-encryptions. This is the architecture of our system ABEBox. It consists of three components: the key management system that provides the secret keys to the users, so it must be a trusted entity, and also triggers the re-encryption operations in the proxy encryption engine. Then we have a client that makes transparent to the users all the cryptographic operations by intercepting the calls to the file system. And finally, we have the proxy encryption engine that manages all the encryption operations, and it can be run by the cloud service provider itself or by any third party that has access to the data storage. So with ABEBox, we decouple the data protection and the access control from the data provisioning and change the trust model in the cloud provider from a fully trusted to a semi-trusted one, because we only need to perform the required operations and to delegate the outdated data. Of course, we have a trusted entity that handle the flexible and fine-grained access control, so it can be good for companies and organizations. And thanks to the proxy encryption engine, we can delegate the revocation, so the encryption, but user keep the access control management. And finally, ABEBox is an overlay system, so it is independent by the storage file system used. In terms of implementation, we use Fuse, a virtual file system module, to intercept the file system calls and handle all the cryptographic operations. With ABE, AttributeBased Encryption, we are able to provide fine-grained and flexible access control, and also handle unknown data recipients. Finally, with the proxy encryption engine, users can delegate the encryption operations while maintaining the access control policies. Here we report the performance evaluation on the reading time as the number of encryption increases. The black curve, called HPRE, is our implementation using ABE of Meyers and Schultz's original solution. The blue curve is our scheme ABEBox with the reverse chain. As you can see, the blue curve is almost constant, while the black curve grows rapidly. In conclusion, what does ABEBox provide? It decouples the data protection and the access control from the data provisioning, relieving the cloud provider trust model from fully to semi-trusted. It applies a flexible and fine-grained access control with the data-centric security, giving this access control back to the users and mitigating the encryption overheads thanks to the reverse chain. If you are interested, you can find a proof of concept of our system ABEBox at the links below. This work has been partially funded by the European project BPR for GDPR and developed in collaboration with the European project Silk Grid. It also recently won funding for future development in the GEAN Innovation Program. Thank you for your attention.